Hello students, this is our lecture number 8 and under today's lecture we will be discussing scheduling queues, different types of the scheduler and the scheduling criteria under the chapter process management. So as we have seen from our previous session what is all about the process state diagram and process control block. So as you can see through this diagram there are new state, ready state, waiting, running and halted state. These are the various states of a process that process will undergo an entire its execution. Next is PCB, which stands for process control block. So PCB is a data structure inside which the operating system will maintain all different kind of information about the process. So with this information we'll move ahead. So our main objective or the main objective of the multi-programmed operating system is to have a maximum throughput or maximum CPU utilization, which means that CPU should have always one program to execute in a uniprocessor system. So through this process state diagram, we can execute more than one task at the same time in a time multiplexed fashion. As discussed in our earlier session, in this time frame between this ready to running, the computer system using this process state diagram architecture, the computer system can execute two tasks at the same time in a uniprocessor system. Like that way, we need to maximize the CPU utilization if it is of a multiprocessor system. So somehow the other we need to always think that we should have somehow the other increase the CPU utilization time. That means increase the throughput of the system, right? Okay. Now as you can see in the diagram, process state diagram, the process will move from one state to another state. As the process move from one state to another state, it is stored in a particular data structure called a queue. So basically I'm talking about the different types of scheduling queues or the queues that each of these state various state in each of these state the operating system maintains. So basically there are three different kind of queues: job queue, ready queue and device queue or various device queue. So whenever a process is created, it is always stored in a new state. So whenever a process is created, it is stored in a new state, that is a secondary state device. Okay, so in that new state, or if the process is in a new state, the process is kept in a pool or job pool where all the set of processes will be there, known as a job queue. So job queue stores all the process that is there with the computer system. And uh, next is the ready state. Okay, so there is a long-term scheduler who is responsible for transferring a job from new to ready state. So when a job is brought or when a process is brought from new state to ready state, it is kept in a particular special type of data structure inside the ready state, that is known as a ready queue. So ready queue is a data structure which is maintained by the ready state for storing all the process that are ready for execution. Now during the execution of the process, okay, now during the execution of any one of the process selected with the help of the short term scheduler, the process might require a IO device, okay, or IO activity that it want to perform. Now in that case what will happen is that the process which is currently being executed and who is demanding for IO activity will transfer that process from running state to waiting state. Now there may be list of different kind of IO device, like some may want printer, some may want keyboard, right, some may want magnetic tape, etc, etc, some may want disk drive. So there are different kind of IO devices based on the demand of the process. The process will be shifted to its respective IO queue. Okay, so basically there are different kind of device queue, okay, that is maintained by the computer system, okay, that is maintained by the operating system. So say for example there are three devices like disk, another one is printer. Okay, or say for example, let us take only two example. One is disk, and another one is the printer. So those are the two devices that any one of the process can use it. These, for these these devices, the different two different queues will be maintained. So for different devices, different queues will be maintained. So in short, there are three different kind of scheduling queues. Job queue, whenever a process is created, all the process will be stored in a job queue, and whenever any process is ready for execution, it will be brought from the new state to ready state, and in the ready state, ready queue is maintained, where all the process which are ready for execution but CPU is not available but ready for execution, those process will be stored in a queue called a ready queue. And during the execution, okay, so the process might request for IO devices like disk, hard drive, floppy drive, or disk drive, optical drive, or printer, etc., or any input activity like keyboard activity. So all those things will be maintained in separate queue. So for separate IO devices, separate queues is maintained. So there are three different kind of device scheduling queues: job queue, ready queue, and device queue. Okay, so now once the process are there in its respective queue, okay, so operating system maintains the information about each of the process using a particular data structure called process control block. So PCB stands for process control block. So wherever we have used, you can see PCB, it means process control block. So there are process which may be in either of these state. I repeat, there are process which may be in either of the process, and the information about such process are stored by the operating system using a particular data structure called process control block, or PCB. So each and every process has its own PCB where all different kind of information will be stored or will be maintained by the operating system. So say for example there is a ready queue. Okay, say for example in a ready state there is a ready queue where there are list of process which are ready for execution, but CPU is not free, so they are kept in a ready queue. Okay, now how these informations are stored, or how these list of processes in the ready queue are stored. So in the ready queue you can see, or the ready queue maintains the list with the help of the linked list. Okay, so there is the ready queue is maintained by the operating system with the help of the linked list. So in the PCB, okay, or in the list of the in the linked list where each node represents the PCB of any one of the process or list of process. So in each of the PCB there is a particular block called where the address of next list is stored. For example, say for example this is our ready queue, okay, and this is our head, okay, and say for example there are only two process that is residing in the ready queue. So there is one block in a first PCB, maybe process number 7. Okay, process number 7 has one block where the address of another PCB is stored. So like that way a link is created between PCB 7 and PCB 2. So this is process number 7 and process number 2. So link is created, okay, and again furthermore there is in the beginning of the list there is something called header. Okay, so header, so head information, this in the head the address of PCB 7 is stored. Okay, in the head the address of PCB 7 is stored, and in this field of PCB 7 address of PCB is stored, and here this is how a link list is made. Okay, this is how a link list is made, and the operating system maintains the information about the queue with the help of the linked list. Okay, so this is all about the ready queue. Now during the execution, okay, or when operating system select one of the process from the linked list of the queue, okay, say for example whichever is there in the first header, that will be selected by the CPU scheduling algorithm and given to the running state. Okay, and in the running state CPU will execute the process. Now during the execution of any of the process, suppose it is demanding some IO activity. Let us consider that it has requested for disk access of disk, okay, hard drive. So hard drive, as I've told already, that in each and every different devices will maintain a separate queue, okay, uh, or separate linked list, okay, identifying which are the list of process that wants to execute this disk. So for example, process number 3, process number 14, and process number 6 is demanding for disk to access. Now they are in the list, right? They are in the list, and these are the list of process who is demanding for disk. So it is maintained with the help of the linked list, as I have discussed already. Now it may happen that process 3 will be getting first chance to access the disk, after that and process number 14, and after that process number 16. So this is how the scheduling queues are maintained by different queues, like maybe ready queue, job queue, and device queue. And for device queue, for that separate device, separate list is maintained. So altogether, the linked list is maintained, okay, for implementing the queue. So with the help of the linked list, queue is implemented over here. So this is how operating system maintains the information about the process. So these are the queues, okay. So we'll move ahead. Now coming to the point, queuing diagram. Okay, so queuing diagram is a representation of the scheduling, how it is maintained, right? How it is represented. So so all the resources of the computer system are represented with the help of the circular symbol. So this CPU, IO, okay, and some process, all the resources, all the resources are represented with the help of the circular symbol, and all the queues are represented with the help of the rectangle box. Okay, so basically, mainly if we are talking about the broad classification, there are two classification that we can see on the scheduling queue. So in that represents that in which queuing diagram it is represents, okay. So those are the device queue and the ready queue. So as you all know that ready queue maintains is implemented with the help of the linked list, from where CPU scheduling algorithm picks up the process and will give it to CPU. Okay, so this is how is the normal workflow. And during the execution of the process by the CPU, so there may be several requirement for completing the process. So one maybe during the execution of the one scenario, maybe during the execution of the process by the CPU, the process is demanding for some IO device. So if it is maybe it is demanding for printer, okay, so it will be shifted from CPU from the running state to waiting state, sorry, one from the running state to IO state, okay, or IO queue, okay, or a waiting queue. So in that separate queue is maintained for the printers, because this process is demanding for printer. So a printer is maintaining a queue, okay. Say for example, this is a queue that is maintained by the printer. So the process who is demanding for printer will be sent to printer queue, okay, which is implemented with the help of the linked list. Now this is one scenario. Next scenario is during the execution of the process, okay, there is a forceful preemption of a running process, currently executing process. So somebody is snatching the CPU from the currently executing process and will be given to somewhere else, okay. So in that case, okay, say for example the time has expired, maybe the process which has to execute, okay, the timer has expired, so it will be snatched, okay, and will be again sent back to ready queue. Again, same was the case of IO activity. Once the IO activity completes, again it will be sent back to ready state or through the ready queue, right? So now it may also happen, another scenario, it may also happen that during the execution of the process, the process creates another process, okay. So using the fork system call, again this is another scenario. Another scenario, maybe any interrupt will occur, okay. So all those, these are the various different kind of scenarios that may happen during the execution of the any process, and this is how we represent in the form of the queuing diagram, okay. So now coming to the point, scheduler, okay. So what is a scheduler? The scheduler is a program. Basically a scheduler is a program for transferring a job from one state to another state. Okay, so there are basically three different kind of scheduler. One is the long term scheduler, another one is the short term scheduler, and third one is the middle term scheduler, which I'll be discussing in upcoming time. Okay, so first let us talk about the long-term scheduler. So the long-term scheduler, okay, so the long-term scheduler basically controls the degree of multi-programming. So basically, when the process is shifted from new state to ready state, okay, who is responsible for transferring a process from new state to ready state? It's a answer is long-term scheduler. So long-term scheduler is responsible for transferring a process from new state to ready state, and it is a degree. It controls the degree of multi-programming because it is who decides how many number of process should be there in the ready queue. So that's why generally speaking, the long-term scheduler are very complex, okay, because it has to have proper mix of types of job that will be residing in the ready queue. So it's a long-term scheduler who is responsible for transferring a job from new state to ready state, and it controls the degree of multi-programming because it will inform to the computer system, or it will do a task that how many number of process should be coming from new state to the ready state. So this is all about the long-term scheduler, right? So now next is the short-term scheduler. Short-term scheduler is also known as a CPU scheduler, and it is responsible for identifying the process from a ready queue, identifying a process from a ready queue, which process should run from the list of the from the linked list that is maintained by the ready queue, right? This type of program, short-term scheduler, is very frequently invoked in comparison with the long-term scheduler. If I have to compare long-term frequency of invocation of short-term scheduler program and long-term scheduler program, it is the short-term scheduler program which is frequently, okay, approximately in every 100 millisecond, okay, the short-term scheduler will be invoked for selecting a job from the ready queue and give it to the CPU. So that is the job of the short-term scheduler: transfer a job, pick up the job from a ready queue to the running queue. Right. So this is all about. Now coming to the point, CPU bound job and the IO bound job. Okay. So although I have already discussed, again it will be a repetition. So there are two different kind of job, right? One is the CPU bound job, and another one is the IO bound job. The CPU bound job or the process will spend maximum amount of time during the computations, okay, maybe some arithmetic or logical computations, whereas in case of IO bound job, spend most of its time doing the IO activity like input and output operations, okay, reading or writing operation, printing it, or reading the data from the keyboard, etc. So such process will spend most of its time doing IO activity rather than computation. Okay, so now why I'm talking about this, because it is very important for performing discussing the performance of the computer system, because in a computer system in a ready state, okay, all the list of process will be there. Now if you try to have, suppose in a ready state or ready queue, suppose in a ready state or a ready queue, uh, the maximum number of process are from the IO bound, okay, a list of out of 100, suppose 80 number of processes are IO bound process and remaining 20. So in that scenario, what will happen is that every time the short term scheduler will execute, there is a very high chance that IO bound job will be selected. Now if the IO bound job will be selected, then there is a very high chance that IO activity will be involvement of IO activity will be more. So in that case, there is a very high chance that CPU will be sitting idle, because it is every time it selects a job, it every time the CPU scheduler or the short-term scheduler selects a job, so there is nothing to execute by the CPU. So it will be again given back to the waiting state for IO activity. So there is a very high chance that in case of if in the ready queue, if the maximum number of job is of type IO bound job, then CPU will be underloaded and IO devices will be overloaded, right? So, and if you talk about the vice versa situation, like in a ready state, suppose maximum is of CPU bound job and minimum less number of tasks, the process is of type IO bound job, then in that case what will happen is that CPU will be overloaded because every time it has to execute something, right? So and IO activity, the IO devices will be, some of the IO devices will be not even used at all because there is no demand of it. So in a ready queue, what I mean to say out here is that in a ready queue there should be proper mixer, in a proper mix of IO bound job and the CPU bound job. The proportion of the IO bound job and the CPU bound has to be maintained in the ready state. So it is a long-term scheduler who is responsible for bringing the job from new state to ready state. So if you don't try to keep it, the proper mix of IO bound job and CPU bound job in the ready queue, so there might be overload and underload situation, right? You have to keep this thing in our mind. So whenever the designer of the long term scheduler has to keep this thing in our mind, that okay, properly it has to select the job from the new state and bring it to the ready queue, okay, or ready state. So basically it's a long term scheduler who controls the degree of multi-programming. Now third one is the medium term scheduler. So the medium term scheduler is responsible for swapping in and swapping out of the process from the ready queue or the ready state. So if you look back to the process state diagram carefully, so I told you that okay, during execution it may happen that some interrupt may occur, maybe timer has over or preemption has occurred for the currently executing process. So in that chain, what will happen, the process will be swapped out of the running state and swapped into the ready state. Okay, sometimes, okay, again it has to be brought from the ready to running. So it is the medium term scheduler here. Medium term scheduler plays a vital role over here for swapping into the running state or swapping out of the running state, or in other words, swapping out of the ready state and swapping in to the ready state, right? So it is the medium term scheduler who plays a significant role for swapping in or swapping out more than one process in and out of the ready queue. Okay, so this is all about the different types of scheduler. And the diagrammatic representation or the queuing, in the queuing diagram, this has been added, you can see, okay, in addition to the earlier queuing diagram you can see this diagram. Okay, so you can add this to that diagram as well. So this is a ready queue which you have already seen it, and this is a CPU, right? So this lower portion we have already seen in our previous queuing diagram. Whenever the process demands for the IO activity or IO devices, it will switch over to IO waiting queue, respective IO queue, then IO activity will perform, and again it will come back to the ready queue. Now it may happen that uh, CPU is executing some process, okay, so preemption has occurred, so it will be swapped out of the process, okay, swapped out and again swapping into the ready. So it is the medium term scheduling. So this is what the queue, okay, that is maintained by the medium term scheduler. So this is all about the different types of the scheduler. I hope you have understood. Now during the entire scheduling thing, right, we need to keep some of the things in our mind, so that the designer of the algorithm, a designer of the system, has to always keep these things in our mind. So first thing is the CPU utilization. So whenever a designer of the computer system is writing an algorithm or implementing some algorithm, others have to think that okay, fine, the CPU has to be maximally utilized. I have to utilize 100% of the CPU. I should not waste any kind of CPU cycle. So maximum CPU utilization has to be kept in on during the design phase, right? Next is the throughput. So throughput means how many number of program is being executed, or how many number of process is being executed per unit time. Okay, so that is known as the throughput. So this is also has to be maximum, and it is correlated with the CPU utilization. If the throughput is high, CPU utilization high. If the throughput is low, CPU utilization is also low. Okay, now coming to the point turnaround time and waiting time, I would like to discuss at one go itself, right? So suppose there is a process, okay, suppose there is a process, okay, I'll just write it out. suppose there is a process P, okay, P1, and the process have arrived at the system somewhere here, okay, somewhere here at this timeline, the process have arrived at the system, okay, in a ready queue. Now it might, when long-term scheduler have selected the process P1 from new state and had brought into the ready state, okay, suppose this is that time. Now it may happen that when P1 have reached the ready state, a ready queue, there is somebody who is executing the task, right? There is some task that is being executed by the CPU. Suppose CPU is executing some task, then in that case, P1 has to wait for CPU to become free. Suppose CPU had become free somewhere here at time T2. So at this time CPU was free, and this time T1, the CPU, the process have arrived in the ready state. So the time elapsed, or time T2 minus T1 is the waiting time, right? So T2 minus T1 is the waiting time. Now at this time T2, CPU was free and has picked P1 from the ready state and has started the execution. So P1 is now executing. So P1 have now completed its execution at time t equals to 3. Okay, so T2 to T3 is the execution time of P1. T1 to T2 is the waiting time of P1. So P1 have arrived at this system in the ready state at T1. Okay, and P1 have completed its execution at T3. So waiting time is T1 to T2, execution time is T2 to T3. So turnaround time is T1 to T3. So if you perform subtraction of T3 minus T1, so it will give you the turnaround time. So I hope you are clear with the turnaround time and the waiting time, right? So turnaround time is the when is the job submitted and when it has completed. The time elapsed between those two time is known as a turnaround time. Now in between during the execution, so in between during the execution, suppose P1 have went for some IO activity, right? Some IO activity also it has went. So during the IO activity, it may have to wait for IO device to get free. So during the turnaround time, all these waiting time and execution time of the for IO devices and all those time has to be calculated, right? So you should not forget the importance of the turnaround time. It is not only for job submission to job completion, which includes waiting time in a ready state, which includes execution time also. Not only those two time waiting time or execution time, but also all IO activity time also you need to include it. So this is all about the turnaround time, and waiting time I've already discussed. Okay. Next is the response time. So in case of time saving system, user will click something and the system has to respond to that request. So the time elapsed between how fast your system has responded to your command, right? So that is known as a response time. So while designing any of the scheduling, okay, maybe a short term schedule or long term schedule, the designer of the algorithm has to consider all these criteria in our mind, so that maximum throughput is um, is achieved with the help of the algorithm, right? So thank you, that's all for today. If you have any questions, please do doubt, please upload the doubt in your post, or we can have a discussion in our next immediate session. Thank you so much.